most of the divide and conquer algorithm, an array of elements as it shows there. Somehow we have to do it slightly differently than bubble sort. And the name itself says, right? We want to get something quicker than a bubble sort for sure. Okay. How does it work? Some introduction here. Okay. By the way, if I remember, I asked last class for any faculty members if they want to teach Quicksort this class, they should get back to me. Okay. I'll probably throw the same challenge for next class. Okay. Keep that in mind. Okay. First, we ask for a volunteer. Second step is we assign a volunteer. If nobody volunteers. Good morning, Aditya. Okay. So Quicksort, randomized sorting algorithm based on divide and conquer. Okay. So remember the standard sort of is what? If you have an array of numbers, if you do bubble sort and all that, what are you getting? Order of n squared. So we are looking for something better than order of n squared. Okay. Merge sort, we said it's n log n algorithm, correct? We saw that. Quicksort is also n log n. Okay, keep that in mind. So what do we do here? We pick you see the numbers there, right? The vertical bar that are shown, there are a bunch of numbers there. Okay. So we pick some random element X. Okay. Now for now, let's call it random. Okay. As we go along, somewhere I think at the end of the lecture of this part, I will say what are good numbers to pick. Okay. And we call that number pivot. Okay. In India, you call it pivot only, right? The pronunciation is pivot. Okay. And then what do? We take that pivot and then we partition that set into three arrays. Okay. 3 separate arrays. As you can see in the second diagram, block diagram there, right? You have L, which has all the elements less than X. You have E, which are elements equal to X. Not just one. If there are two X's, there will be 2 there. Don't get the mistaken impression that is one element array. Okay. And then G, element greater than X. Okay. Divide and conquer, what do? We have recursion, remember? So we divided, we do a recursion. There is no recursion required to be done in E, right? Because they are all equal. When the values are all equal, there is nothing to sort there. Okay. You recurse on L and you recurse on G. So when you go to the bottommost layer, by the time, just like in merge sort, they'll all be sorted. Then you join L, E, and G. That's it. It's as simple as that. Let me pause here. Anyone has questions on that? Is there anything that you don't understand in that slide? Do you begin to see, student, the difference between how a bubble sort works? What did we do in bubble sort? I think we found the lowest element, put it in the first location, right? Or we swap it. I think we swap the lowest with the highest, right? Something like that we do. It is so bad I don't even remember bubble sort now. So you can see how people think different ways, right? So it's a great algorithm. Let's continue. Okay. So how do we partition, right? So it gives you some kind of an algorithm, how you are going to come with L, E, and G. Okay. As you can see the pseudocode on the right and some explanation on the left, right? So we remove in turn each element Y from S. S is the given array, right? That is the input sequence. Okay. And then we put that Y into either L or E or G. Okay. This is pretty standard, easy C code for you to to figure things out, right? Take an element from an array and put it in one of the arrays. Okay, and you name the arrays left, equal, or greater. LEG came from less, equal, or greater. Okay, and then how do you do that? You compare it, right? So you know how to declare an array. You know how to declare 3 arrays. Okay, and then you know how to move an element from one array to the other array, right? Is there anyone who does not understand those 2 bullets, sub bullets of bullet 1? Okay, now the proof is in the pudding, right? If I click on participants to see the video, I'm sure my system would hang. Before I do that, before I take a chance, let me give you a quick in-class exercise right now, right? Because I did not see anyone raising any hand or saying I have a question, right? So here is what I want you to do. Okay. So take a piece of paper, faculty members, please coordinate that. Okay. Please coordinate this small exercise in the class right now. What I want students to do, groups of 2 or 3 as always, take a piece of paper and pencil, declare, I'll put it in the whiteboard. Where is the whiteboard here? I need my whiteboard. Stop sharing and my whiteboard will come. This is what I want you to do for those 3 lines of code. Declare me to do 3 arrays left, equal, and right. Somebody has finishes it in 5 minutes. Please say so in private mode with me. Put it in the chat for me in a private mode. Voice is looping because participants I did not mute all. Okay, I muted everyone.
Not right here. Then what do you do? Then you take L of I gets S of I. You all agree? Right? Because it's less, we put that element, whatever is in S of I, we put it in the left array. Okay? Now, do I need to increment the left array counter index is what I'm asking you. Or this I would take care of that for us. Because what happens is we are anyhow looping I, right? We are already doing in the for loop, we are saying for I equal to 0, I less than 7, I plus plus, right? So that I is getting incremented in that for loop. No whiteboard again. People are seeing whiteboard, but once I type it, they are not seeing it. Okay. Okay, got it. So what I can do is I can open up my notepad. Bear with me. Okay, now you see my screen. Okay, good. So Sri Prakash wrote a for loop like that, correct? Then you say if S of I is less than X, what do? You say left of I gets S of I. Okay, else S of I greater than X, not question mark, greater than X, then right of I equal to S of I. Sounds right, correct? The question I'm asking is, after I write S of I less than X, left of I equal to Xi, do I need to increment the counter for the left array or not is what I'm asking. Font size is small. Okay. Font size is small. A counter or not? Similarly for right array counter or not? For incrementing index variables, we use some variables, correct. So that I is the index, right? So in this for loop, we are already incrementing I. Okay. However, somehow you have to figure out how to increment the left index and the right index too, right? Think about it, because you cannot simply use the same I for both of them, because sometimes it goes to left, sometimes it goes to right. Okay, so you need to have a variable. You need to have a variable somewhere which would allow you to keep track of the index which is available in left array and the index which is available in the right array, right? So this is not really I here, this is something else. Left array could be left index. I can call it Li. That could be index of Li. And then right array could be, yeah, there you go, you got it. Okay, something like that, you got it. Perfect. Okay. Basically plus plus, exactly. Li and Ri. And then you can say you want to do Li plus plus, because as you are assigning it, but initially it is not really Li plus plus, right? When you're doing it for the first time, it's not L, it's just Li. And correct? Whether it's Li or just Li plus plus, you figure it out in your debugging, okay? Okay, now let me go back to the lecture. So beginning or at the end of a sequence, and it takes only log of one time, because you're not search of an array, right? That's why it's of order of one time. Okay. So when it's order of one, when you have n element array, the partition step of Quicksort takes order of n time, because how many partitions you do? It's a factor of n, right? It's proportional to n. That's why it's of order of n. You can see here, whatever we try to write there is what this while loop is showing. While s dot is empty, right? You continue to do this one. You do the comparison. If y is less than x, you insert into the left array, or you insert into equal array, or you insert into the last array, or right array, or greater array. Okay. Now let me show you some execution. Okay. So generally, once you get deep into it, you'll actually see that this Quicksort is shown as a binary tree representation wise. Okay. The root is the initial call. Okay. The leaves are calls on subsequences of size 0 or 1. So as you keep building the tree, as you keep partitioning, you keep building the tree. Okay. I actually have animation here. So we did it 2, 4, 3, 1. Okay, you can see how, and then you're taking again, partitioning it like that. Okay, going down to the bottom. Let me bring it here. 7, 9, 7 are in the other partition. Okay, so 1, 2, 3, 4. Okay, 5 should be, there is no 5, right? 1, 2, 3, 4. And then you have 7, 9, 7. So there are two partitions here. Okay. And then he took the pivot as 6. See that underline there? Pivot is 6. So anything less than 6, you put them in the left side. Okay. So as you traverse through this one, what did you get here? I mean, the animation is a little bit screwed up here. when you take a partition number 6, anything less than 6 has been put in the left side. So as you're traversing, you get 2, then you get 4, then you get 3, then you get 1. So that's what you see in this thing here. 2, 4, 3, 1. Now 7, 9, and then again 7, go to the next one. Okay. Now once you get 2, 4, 3, 1 here, for a second, stick to the left-hand side, you're taking a pivot again, right? Whatever pivot you take, I think they're underlining the pivot. 2 is the pivot. Anything less than 2, you put that in a separate box by itself, that is 1, okay? And then anything greater than 2, which is 4, 4, and 3, right? You put that in this box, and 2 is in the middle here, okay? Now, when you come to single element, there is nothing to pivot. Now, when you have 2 elements, you pivot 3, whether you take 3 or 4, it doesn't matter. Each of them gets, so the leaves ultimately become your nodes, which you take them, okay? Then you merge them back together and sort it out. It is the thing here is, right, when you are doing this quick sort, right, then we have to do the complexity analysis. Why is this better than the regular sorting algorithm like a bubble sort or a selection sort? Okay. So there are 2 cases. What is the best case for it and what is the worst case for it, right? Now, if your array is divided exactly almost half, right, the moment half means we know it is binary. Now, what does binary means? At every division, you're eliminating half of it, correct? Now, we already know when anything to do with binary, the complexity would come to log n base 2. Okay, so recursively, as you're breaking it down, remember when we had the 16 element array, I showed you in the last class when we broke it down, the tree levels were 4 because log of 16 to the base 2 is 4. Okay, that's number 1. Okay. Keep that in mind. Sorry, let me go here. As you can see here, how we are partitioning it into half and half and half and all that, okay? Now, when you do that, right, so the depth is going to be log 2n, okay? Now, at each level of the recursion, right, whatever work that you're doing is going to be the order of n, okay? Because all partitions do work that is linear. Because you whatever searching you're doing less than or equal to, because that's what we are doing, right? You're picking a pivot, which is order of 1. And then you are looking at less than that pivot, equal to, or greater than. If there are n elements, there are n comparisons. So that will be n, order of n. So then the total would be order of n times order of log 2n. That is the reason why we come up with n log 2n, which is better than n squared, right? Anywhere you have a log, that's a better option. Okay, that's the reason why we say complexity is order of n log 2n. This is a very legitimate exam question, by the way. They can say, discuss why a quicksort algorithm is a n log n algorithm. Okay, so you should be able to explain that, hey, in a quicksort, in the best case, only in the best case, it's an n log 2 algorithm. Okay, in the worst case, it's something else. We'll see that shortly. You should be able to explain saying, hey, in the best case, the array is always getting split into 2 halves. Okay. And now, and that is the concept of binary, and as you go down recursively through a binary tree like that, we know the depth is going to be log of n. That is the log n term. Okay. Now, at each level, depth meaning as a recurse, you keep building the tree, right? Okay. Whatever work you're doing to compare, to break it down further, it's order of n work. So the total work done for the entire tree is, you have O log 2 depth plus at each level you have order of n work. That is why it's an n log 2 algorithm. Okay. Now, let me go to the next slide. Always divide the size and array into 3 parts. Okay. So you have a length of 1 part containing the pivot. Remember there are 3 parts, right? So you always have the pivot. And then you have a length 0 part, meaning there is nothing less than that pivot. And then you have n minus 1 part, meaning it contains everything else. Okay. So there is no recurring on a 0 length part, right? Obviously, it's a no-brainer. Okay. Now you recur on the length n minus 1 part. Now, if you take the n minus 1 part also as the worst case, the same problem repeats over and over and over again. Right? You'll always have a 0 length part, you have 1 part, and then n minus 1 part. Okay? This is the worst case because you're basically dividing into single element. See that one? Like that. You see, left is single element, all the other partitions. One more single element, rest of the thing in one array. So essentially, what do you have? You will have an n depth, right? It's no longer a log 2, correct? Log 2 is binary and you're dividing nicely into half. But here you're not dividing into half, you're dividing into 1 and rest of the tree. So to really go all the way down, then if it's an n element array, you will have depth of n. Now when you have a depth of n, and at each level, your order of work is order of n, because it's an n element array, right? So what is the total? N times n. That is n squared. So the worst case would be order of n times order of n, because at each partition level, you are doing order of n work, and the number of partitions, the depth is n. So n times n gives n squared. Okay, let me pause here. Questions, comments? Do you understand the difference between the best case quicksort and the worst case quicksort? Here is the time to ask questions. Right? So in those cases, if the array is sorted, when you break it down, you will see that everything is broken down to one element array basically. Okay? It's either sorted or inversely sorted. If it's inversely sorted also, you will have the same problem. A little bit of theoretical way of explaining what I just explained. I'll skip this slide. If you read it, you'll basically come to the same conclusion. That's an order of n squared algorithm. Okay. Now here's another slide that I put. I thought this will be useful for the students. Is what is a good pivot? What is a bad pivot? So typically when you're getting the data split evenly, it's a good pivot. If the data is splitting, like you see the bad call thing where you have one element array and everything else is stacked to the other side and recursively that happens, that's a bad call. So from a simple arithmetic type numbers perspective, what we are saying is if you have a series of numbers like 1 through 16, typically good pivots are those things in the middle. Doesn't have it as one exact pivot, okay? As long as the sets are distributed evenly based on your pivot, then it's a good pivot, okay? Okay. Skipping this for now, you can review it and then we'll discuss it in the community, okay? What is InPlace Quicksort? Basically, InPlace Quicksort, I'll give you one sentence and then we'll move on. InPlace means we are not creating that element, the other arrays to do that, okay? We can do that partitioning in the same array itself, okay? That's what InPlace Quicksort is. We'll discuss this more in the community to save time here. Okay, I do have some nice graphic here. You can see this, how the elements are being swapped in the place. In place means in the same places we are swapping. Okay. Okay. So here is some Quicksort notes. If the array is already sorted, then it's going to be an order of n squared algorithm. Okay. Most of the time it's n log 2n. Okay. And even till today, people say Quicksort is generally the faster algorithm known. And when you become a programmer in the real world, you'll be, if you have to do a sorting thing, you will quickly learn to use Quicksort to do your sorting. Here is some summary of the sorting algorithms. You can see selection sort, insertion sort, they are all n squared algorithms. Quicksort typically is n log n. Merge sort also is n log n. There is some comparison that is done where to use merge sort, where to use Quicksort, and things like that. I'm leaving that discussion out from this class for students who are interested, or if you can go, maybe I should give that an assignment, right? Do some searches and put in the community when to use merge sort and when to use Quicksort. Okay, that will be a good community assignment. Okay, go do some research on that and post your answers in the community for rest of us to learn from it. Okay, not covering heap sort here, but somewhere in this class we'll cover, because I didn't introduce it to heaps and all that yet, right? So once we do that, we'll cover heap sort. Okay. So rest of the time, this is what we are going to be doing. Okay. Let me see. I didn't keep track of the time. What is the time now? Yeah, another 20 minutes, right? Same thing. As always, the last 20 minutes is devoted to doing some exercise, right? So I posted this in a text file in the community. I wanted faculty members to print out copies. I do not know if they have already done it or not. Please go to the community. Let me go there. Yes, Sri Prakash, you're right. In Kruskal's algorithm, we can learn heap sort. So just like how we declare an array of 7, declare something like that, and then trace the code. Your data is initially you declare an x of some value, okay? Where it doesn't have to be 20, it can be 5, 6, 7, whatever. When it says printf, enter size of the array, in your trace, what I want you to do is you can say something like this in your trace. How does the output look, right, in the trace? Okay, so when you say output here, so I say printf enter size of the array. So my output would be initially enter size of the array. You're seeing my screen, right? If you're not seeing my screen, put it in the chat. Okay. Then when I go to my code here, I say scanf %d size. So my size variable will have whatever size I entered. Okay. So somewhere here I can put some notes. It's not really output, right? It is in your program. There is output, screen output. Here inside the program, what is happening? Okay. Size gets what? Enter the size of the array. I enter, let's say, 5. So my size variable will get 5. Okay. I'm assuming you learned how to trace code, right? And then you say printf, enter number of elements, comma size, right? So you're entering the number of elements. So you'll see in the output. Enter number of elements, comma size, I think, right? That's what we said in the code. Okay. So you're going to enter number of elements and size, and then you say for I equal to 0, I less than size. Let's say I entered size again, same thing, right? 5. Earlier I chose 5, right? So you are going to scan all the elements there, and then you are going to call the quicksort algorithm. Okay? So now all these things will happen, this set of statements will happen only after quicksort happens, right? So here is the quicksort code that I gave you. Sorry. This is my quicksort code. In text file, it will be much clearer because the font would be higher. Okay. So take pivot, whatever the pivot element is, right? Slightly different algorithm here. Okay. So you follow this code and then see what the values are first and last, right? And you call those elements and see how the code works. If you take a size of array size of 5, put them in unsorted one, trace all the elements of the array, and by end of going through this loop, because you have quicksort x 0 size -1, you will be running that code 2-3 times easily, right? Depending on the pivot, it's a log 2, right? So log 2 means 2 raised to 2 and plus 1, so 3 basically there. So you go through, input those values, and see that at the end of this program, you will get your sorted array. Okay. Is there anyone who does not understand the task? All you have to do is take an array element of say 5 or 6, put some values there, and go through the code. Simple, or worst case 6. Okay, and then you tell me what is the complexity that you get after you do that. It should be, I mean, it depends on what type of array you took. It should be n log n. If you choose bad pivot, if it's a 5-element array, it's n squared, that is 25. So you have to trace it 25 times. Okay. Faculty members, please coordinate. Somewhere here, I had my code sample of this here. Can I view? No, maybe. Okay. I should start removing empty spaces so that you guys can see the code, right? Otherwise, how will you see the code if I increase? I should reduce it now to 16. Format font. If I say 14, I think it should say, okay, I think this should still be good. This is too small, maybe. I'll make it 12. Yeah, that should be good enough. You have the full code there, okay? Okay. I'm done with the lecture part. Go ahead and do that, and then we'll do the next chapter. We'll begin unit 3 next class. I should say raise your hand. Maybe half the class will raise their hand.